Hello, everybody. My name is Anshul Sharma, and I'm from the Electrical and Computer Engineering Department at the University of Florida. This project is about my final project at the Wireless Communication System course, and I will be talking about the topic using space-time block coding, that is STBC, to improve the communication reliability and efficiency of a MIMO OFDM system. This presentation will cover all the aspects of it, beginning from the motivation as to why I chose this particular topic and discussing about all the vital parts of MIMO OFDM as a system together, space-time block coding, and the results and inferences after simulating the mathematical models. So let's talk about the outline. So the outline in here would cover the problem statement, that is again the motivation of behind choosing this particular topic and why it is supposed to be researched upon in the coming future and what are the current demands. Then we will talk about OFDM in detail. After that, we will also discuss MIMO as a separate system. And then once we have the basics of OFDM and MIMO separately, we will talk about OFDM-MIMO system in together. Next would be space-time block coding that we have to like incorporate with the OF-MIMO DM systems, and what happens after that, the results and inferences, the final conclusion that we received after seeing the graphs that we generated using the mathematical models, the conclusion, and finally the demo of the project. So let's begin. The problem statement. So the motivation behind doing this project was that in current scenario, in today's world, high data rate transfers are demanded by most of the applications. And a current research study in wireless communication systems predicts that this data rate will be increased by almost 1,000 times in the coming future. And the most important challenge for the upcoming technology would be handling the interferences from different sources while achieving maximum communication reliability. So there is a need for an excessive increase in spectral efficiency to meet the increasing demands of the customers of next generation. Whereas keeping the huge amount of data in mind, there has to be a way to improve the reliability. That is one of the most important issues of wireless communication system, and to keep the originality of the signals at the same time increase the system throughput. So let's begin by talking about the most basic OFDM. So OFDM here stands for orthogonal frequency division multiplexing, and it is a multi-carrier transmission technique which is based on the theory of frequency division multiplexing, that is which was introduced after the 3G era to improve the link capacity overall, but later on it became like a very vital part of the current generation wireless technology. In this technique, really closely spaced subcarriers are used to carry data on several parallel data streams or channels. That is why it is called a multi-carrier frequency technique. This helps in minimizing the signal fading as much as possible, whereas it also helps in mitigating the ISI effect and provides really high enhanced data rates. We will see the working of the OFDM system in the next slide. Let's go through the block diagram. So here is the block diagram of the OFDM system. First of all, the data in here is fed to the serial to parallel block, where the entire serial data is converted into a set of parallel data blocks. Then it is these set of parallel data blocks are fed through the constellation mapper, which is nothing but a modulator. This modulator can be of four types, that is BPSK, binary phase shift, then QAM, amplitude modulation. And this data needs to be modulated. So once it is modulated, it is passed on to the IIFT block, whose prior and most important work is to orthogonalize the data. So eventually, the proper channel after the proper channel estimation and modulation, the transmitter in the frequency domain will treat these streams of source symbols that come out of it, and they would be the input to the IFT block that changes it into the time domain. So it basically takes n number of symbols that are the total number of subcarriers, which are the multi-carriers basically, and provides n orthogonal sinusoids. Each of these outputs have a different frequency, hence it is like called the multi-carrier frequency technique, which has a different orthogonal frequency onto it. And once it comes out of the IIFT, then it goes on to the parallel to the from the parallel to serial conversion block, where it is converted again into a total one serial signal. Once that is ready, it is fed on to the channel, and the channel sends it down to the receiver. After the receiver receives it, the entire reverse process happens by first deleting the cyclic prefix and then reversing the IIFT time domain back into the frequency domain. Once we get the frequency domain parallel signals, we equalize them and send it back to the constellation demapper, where the entire demodulating work occurs. After demodulating the entire signal and getting the parallel data, we convert it finally back from parallel to serial to get the original set of data that was passed to the OFDM system. This is the basic way of how OFDM system works and how the data rates are increased by using the multi-carrier frequency technique. Now let's talk about MIMO systems. So MIMO systems are defined as multiple input and multiple output antenna systems, where there are several sets of antennas at both the transceiver and the receiver end. The point of having these sets of antennas on both the ends is to have multipath between these antennas, allowing the signals to be received at different times on different antennas. Thus, the concept of the multipath fading would be to increase the speed and to increase the capacity of holding the data, and reducing the fading effect overall. So the data rate would increase directly in proportion to the number of antennas that we use, because that is pretty obvious that the more amount of antennas you have in there, the more amount of data you could like probably send to it. And this is one of the most important parts of wireless, 4G wireless in the current gen that we use, like Wi-Fi, LTE, and LAN, and some of the other stuff as well. So let's see how a MIMO system basically works. In the diagram, you can see that there are two sides, the transceiver side and the receiver side, and there are like four antennas onto it. Assuming that one transmitter antenna, that is the number one antenna on the top, transmits to all the possible receivers. So we have receiver 1 receiving signal from antenna 1, 2, 3, and 4 at the same time, receiver 2 also receiving the signal from like 1, 2, 3, and 4. So if assuming that if we just need the signal from antenna 1, then the other signals are nothing but interferences coming from the other antenna. Suppose if antenna receiver side antenna 1 wants the signal, just looking at the signal coming from antenna 2, then the signals that are actually the red, blue, and green coming from the 1, 3, and 4 are nothing but interferences. This does overall increase the problem of reliability, at the same time does more amount of signal fading when we increase the amount of antennas. So to like in systems where we need to use MIMO configuration and not MISO is basically nothing but multiple input, single output. Here, most of it, the output is single. So basically, the antennas are sending the signals in the form of beam forming. But in case of MIMO system, where we have multiple signals coming in, and the signals that are not required do nothing but interfere and reduce the signal quality, thus increasing the problem of reliability. So when we increase the amount of number of antennas in systems where we need huge MIMOs like 8 by 8 or probably 16 by 16, these interferences also keep increasing a lot. And we need to find a solution where the problem of interference is solved. Like if antenna 1 has to just receive the signal from antenna 1, and the other signals coming from the other antenna should not be able to interfere in the same. So let's see how are we going to deal with that. But before that, I would want to talk about OFDM and MIMO system in together. So when we combine the OFDM and MIMO system together, it becomes the backbone of current generation wireless systems such as LAN and LTA. This is the most commonly used configuration for the wireless comms in current gen. The OFDM system, when used with multiple antennas at the transceiver and receiver ends, leads to the OFDM-MIMO system. Excessive increase in performance gains and spectral efficiency when they are used all together. And as we already spoke about, the number of antennas are directly proportional to the interferences caused. So when we move to the higher order MIMO OFDM system, the problem also increases at the same rate, and the reliability and signal fading is something that has to be taken care of. So we would first try to simulate the OFDM MIMO model, and on MATLAB, we will first generate a mathematical model and simulate it on MATLAB to give us the results for a 2x2 and a 4x4 MIMO. So yeah, I have done that. MATLAB code online really has helped me a lot finding out how to go about it. There are several examples where I went through and found out what I wanted to do with this project. So let's see the simulation that I performed on MATLAB and what results I got for it. So the blue line in here shows the 2x2 MIMO OFDM configuration, whereas the 4x4 is shown by the red. You can see that there is bare minimum difference in between two. When we're talking about 35 dB SNR, the BER, that is the bit error rate here, is very close. It's somewhere like in the range of 10 to the power -1. But we see that there is a slight improvement when we are using a 4x4 MIMO as compared to the 2x2 MIMO. Because there is like, as we increase the capacity of the more amount of antennas, the data rates are faster. But as observed, when we go to the 8x8 MIMO or 16x16 MIMO, the data rates, like the BER drastically, like it gets very high. It goes to the order of around 10 to the power uh, 0 or something like that, because that is when we're using an 8x8 MIMO, the interference in that case increases a lot. And if you're talking about one antenna being used, there are seven other antennas interfering with that one antenna. So we need to find a solution of how to deal with the problem when we have a bigger my OFDM system like 8, 18, or 20. I can't simulate that, because that would take around a lot of time and a lot of it could not get that on the code running. But this is the proof I've used from the couple of papers, that if you use 8x8 or a 16x16 MIMO, the error rate will increase by approximately, like, it would go up to 10 to the power 0, or even like very close to 10, almost in the tens. So let's go and see as to how we could solve this problem. So STBC with MIMO OFDM. What is STBC? STBC is nothing but a channel orthogonalization process which removes the multiple access interferences and hence reduces the coupling effect. So the interferences coming from the other antennas need to be taken care of, and this is one of the best proven techniques in the history to be taking care of that problem. It works in a way where it uses various received versions of data streams at the transmission end, and it improves the overall reliability. So it basically believes in using redundant data that comes at the end of the transmission, and getting a weighted average of that. So if I received, so there are several antennas, suppose there are like 5 antennas on the receiver end, it would receive all the 5 redundant data coming from the one that are causing the interference, but eventually towards the end it would get a weighted sum, thus reducing the interference and giving you an overall the most reliable possible data ever. So here the data streams are encoded as blocks, these space-time block codes are presented in the form of a matrix. And one of the most best-known MIMO coding scheme, STBC, is called Alamuthi scheme that we have discussed in class as well. So, what is Alamuthi scheme? Data to be transmitted is to be spread between the number of antennas. Let's consider a 2 cross 2 MIMO, and let's consider the incoming symbols as C1, C2 coming up to Cn. Here, the matrix for the 2 cross 2 will be represented in a form that you can see in the picture. And C1 and C2 and minus C2 star and C1 star. So the first row is basically representing one time step, and the second row is representing the second time step. So Alamuthi scheme and this particular code is known to achieve the maximum diversity and data rate of 1, because we are able to why a data rate of 1, because we are able to transmit two particular symbols, that is C1 and C2, over two time periods, two time cycles, thus getting a data rate of 1. This is like the best achievable data rate possible given by Alamuthi. And let's see, in the first time slot, C1 and C2 are assumed to be transmitted by two antennas like separately, simultaneously. On the other hand, in the second time slot, minus C21 and C1 are transmitted by the two antennas simultaneously. Thus, like as I said, eventually, though it is getting redundant data, it is getting a weighted sum in the end. So when we are talking about the received signal after processing, it would produce a maximal ratio combining result, thus getting the best out of the best. And the channels are orthogonalized and the weighted sum of the result is obtained. This is again plotted mathematically, and there is a model that was simulated on MATLAB using the communication blocks of MATLAB provided by the MathWorks website. And the results here are compared in the next section. So as you can see, let's first compare a 2 cross 2 MIMO OFDM system. So what happens when we use STBC and we do not use STBC? So the blue line you can see here is the 2 cross 2 MIMO OFDM system without the use of STBC. So you can see the error at 35 dB SNR is in 10 to the power minus 1. That is pretty high for a 2 cross 2 MIMO system. Whereas when STBC was employed with the OFDM-MIMO system, we had error rate shooting down to 10 to the power minus 5, which is a huge improvement overall for a 2 cross 2 MIMO system. So eventually, the error rate goes down by approximately 10, like in the magnitude of 10, around from 10 to the power minus 1 to 10 to the power minus 5, and the error rate overall, it gives you a very huge diversity gain when using it with STBC. So this was one of the results of the graph that was calculated. On the other hand, when I calculated and simulated a 4 cross 4 MIMO OFDM with STBC along with the 2 cross 2, I could see that there was a huge improvement in the overall diversity gain of the 4 cross 4 MIMO, as you can see in the figure. And it gave like a really less error rate at like a very great SNR. So the diversity gain was very high. So just imagine like when we are talking about a 4 cross 4 MIMO, like we are getting 4 redundant data, which is giving you a weighted sum that could be like as close, that would be a better option than getting a two process redundant data and then getting the weighted sum, as you can see in the picture. So as we go up, as we go in the higher order, when we go to 8 cross 8 or 16 cross 16, then we're getting like 16 redundant data and we're getting a weighted sum. So we're getting the most closest possible value out of it. Thus, STBC with a higher order MIMO systems is a great idea, and like there is a huge improvement in both the error rate as well as the diversity gain of the OFDM MIMO systems. Hence, it is a very efficient technique to be used in the current generations as well as in the generations coming in the near future. So that's all about the results that we simulated. And now I would like to talk about the conclusion. So the amount of interference increases in the higher order MIMO, as we saw and talked about, and a lot of a literature survey has also given an evidence that as we go above 16 into 16, the error rates go very, very high. There is not much of a difference in a 2x2 and a 4x4 MIMO of the system performance, because we're not talking about STBC. We're talking about just the OFDM-MIMO like together. There is not a lot of improvement because there is a lot of interference coming from the 4x4. And once we do the OFDM-MIMO with STBC, you saw the improvement that we achieved in the last graph. There was a huge improvement that we saw. And the huge system throughput achieved by employing orthogonal STBC with OFDM-MIMO system, the error rate almost decreases by several magnitude of 10 from 10 to the power -1 to the power of -5. And eventually we have a better diversity gain when STBC is used in higher MIMO configurations. So this is how I would like to conclude my project with that STBC is a great technique to improve the communication reliability and efficiency of a system in terms of performance and diversity gain, as well as in terms of BER and SNR, that is reducing the bit error rate drastically. So let's go through the final part of the presentation, that is the demo. So I'd already kept this running. This is the code for OFDM-MIMO. Here I had generated the modulator as we spoke in the block diagram, the QPSK modulator, demodulator. Then we generated the pilot symbol that go through the IIFT. And this part in here is to set up the number of antennas we're trying to compare it for. Once the pilot symbols are set up, let me run the code first. Once the pilot symbols are set up, we again pass it through the FFT, and the FFT gives it to the serial part. Then this is the OFDM modulator demodulator, and then hence after that we generate the AW, we pass it to the orthogonalized channel, and once the channel is done, we generate the data and start the simulation with really flat fading channel, get the frames, number of frames we try to plot it on, and then eventually once it comes, we try to convert it from serial to parallel, and eventually plot the BER versus SNR. As you can see, this is for the 2x2 MIMO, which is only the OFDM MIMO. And let's see the OFDM with the STBC. This is for the OFDM MIMO STBC code. It starts with the same as we spoke about the OFDM MIMO OFDM system, modulator, demodulator, added the pilot symbols, went through the case, generated the matrix, then the OFDM modulator, demodulator, generated the MIMO channel. After the MIMO channel, we construct the OFDM frames, the number of frames we want to transmit it for. Then we find the STBC, we put the STBC coder encoder. We first generate a couple of random numbers, which would be the random number symbols that would go into the OFDM or the QPSK symbols using the OFDM modulator. Then it goes into the STBC encoding, decoding. And we get, once the decoding is done, it comes back to the demodulator of the QPSK, and we generate the error statistics and plot the BER versus SNR graph. Let's see, let's generate it for the OFDM MIMO STBC. It's gonna take a little time because the frames are like 1200. It says busy in here, so yeah, we have to wait a little. I really enjoyed doing this project overall because the results are really, really great to see, and you can see like whatever theoretical stuff we cover, it pretty obviously like these results are really, really, it goes by what has been promised in the literature survey. You can go through the code. I've submitted it online, and also, the MATLAB MathWorks website has been really, really helpful. The communication blocks have been taken from there. The code has been also mostly taken from there and modified for the use as possible. And let's see, still busy, it's 1200. Sorry for the delay. So there we go. This is the curve for this time. I generated it for like the 1200 frames per second frame rates, frames overall, and last diagram I generated it for 1000 frames. So this is your 2x2 and this is your 4x4 for the OFDM-MIMO with STBC. I hope you enjoyed watching this video, and I hope all the information provided in here was helpful. Thank you. Thank you.